talk about a circuit and talk about how we start to apply control theory around this sort of circuit and how we sort of look at this in a formal setting. Now I'm going to look at this sort of circuit here, L, R, and C. And basically when I look at this, this could be a core circuit that I'm actually trying to control. It could be a prototype of a physical system that I want to kind of look at. Now I have three sort of elements here, but I also have a buffer. And the buffer is really useful because it allows me to then, not disturb this output in terms of in terms of actually seeing it. On the other hand, I can't actually disturb the output, so that might be an issue too. But I have here a very much a single input, single output system that I'd like to be able to figure out what's going on. Now I've made the resistance negative. That is actually a physical thing. If I have a negative resistance, I can in fact get a transfer function out of it. That's usually the easiest way to think about it from a circuit because I know it's linear. I'll just kind of use Laplace for this. And then I can then take from this and I can write my differential equation. I also know that I've got a time constant, which is LC, that sits in the second order term. RC, which then allows me to talk about the Q. Of course, effectively now that's going to still, it's still going to be a nice quantity of terms, but I'm still going to get a negative sign once I've normalized time down here. And you really want to normalize time. You want to normalize everything you possibly can, both if you're doing numerics or if you're doing analytic work. It keeps the possibility of errors and problems and issues showing up. It just really minimizes all of your issues. It also allows you to say, I can scale this across many different kinds of things, and it all gives me the same system. Solve the problem once, everything works. So once I start with this equation, now the question is I want to then say, can I go into a linear equation system? Well, I'm going to define y1 as the derivative dv dt1. This allows me to deal with the second order term. And as a result of that, I can write down a vector here and then write down my linear equation system. Well, I'm going to have something that's just going to be my state matrix A. And I'm going to have a B matrix because I have the one input. It affects the one term and not the other. And then I'm going to have my C matrix. There's no feed through here, just my C matrix on this particular term. Great, so now I can actually have the system defined. I can now try to say what would happen with the circuit in what now seem to be fairly straightforward components. In fact, I have one parameter and only one parameter, and that's A, and that's really a question of what is the quality factor of the system. Cool. So given that, I can say, well, okay, is this stable? And the answer is no. It's not stable at all. It is, in fact, is not only unstable, but you have two positive roots because this quantity in the square root is always smaller than A. So the positive root is always bigger than 1, and the negative root is always then, when I put it together, it's always not bigger than 1, it's always going to be positive. The second one is always going to be positive. One will be close to 0, but the other one will be much bigger. So I got to deal with those two things. You say, great. Well, let's say, could I control it? Well, that would be great. My controllability matrix I can then generate. Again, I know where my B matrix is, so that starts there, and then I get the extra vector for the second vector of it. It turns out this is full rank, and in fact, it turns out the eigenvalues are fairly reasonable in this case. And in fact, for a different value of A, I'm going to probably get 1 plus and 1 minus. They're not going to be crazy off in magnitudes. But there will be some separation there, but I should be able to get a pretty good handle on this, depending on what A would actually be in the system. So if I had both steric variables, that would be, I have V of t, yay, I've got that, but what's the other one? Well, V1. Well, that's kind of a representation. What's that? Not sure. If I had actually the current in the inductor, which is maybe one physical representation of the state variable, I could do that too. I don't have that. So I'm going to have to estimate. I'm going to do some sort of system estimation. Fortunately, I know the circuit. That's good. Having the circuit means I could now at least, I could create my system. But now I got to say, well, okay, given my system, can I actually do that estimate? Well, now I need an observability matrix. And it turns out that's actually a pretty nice matrix. It turns out identity matrix, I know my eigenvalues are both 1. So I can very nicely build an observable system here. And at this point, you could say, all right, now I could try to do LQR and LQE to try to find what it would be my optimal regulator, I can also figure out what is my optimal estimator. Great! So in this particular case, I probably would say sourcing voltage and measuring voltage about the equal cost. It's not going to be much different either way. And so then I'm going to be able to use that. And from that point, what happens is then I say, okay, they're equal. I can actually then set up my Riccati equation. Everything is great, right? Because I know Q will be an identity, R is an identity, which definitely simplifies things. Q is just an identity. And I can just solve it. And it's this nice 2x2 system. This immediately begins to get the point of, well, how complex is it going to be? Well, my vector is then going to be B times P. So B is going to come into this. That means my KR vector is going to be a vector times with some P. Well, the two variables I'm going to care about is P12 and P22. I can go through and try to solve these. Remember, P is symmetric, so P12 and P21 are the same. And so I could actually go in and try to solve these equations in effect. Knowing that there's an interesting symmetry here, I can do that. I can see the multiplication of those two terms for the last factor is here. Phew. Well, it turns out then I can actually do some solutions for P12 and P22. And yeah, I can get it. And you're like, that's cool. So we can actually find out what that regulation would be depending on what A is. I definitely need the estimation as well, which means I'm now creating a whole nother structure, which is going to depend a lot on what is the noise out of that resistance. And I can start creating the same matrices. And from this, you could actually say, well, okay, now I could build a whole network that could then, given I have Y of t, I should hopefully be able to control the system through the U of t. Seems kind of complicated. But it's in fact how the flow works of how you can do this optimal control, because then you can say, well, I know given the metrics that I picked and given the noise in my system, it is in fact an optimal system.